Today we're going to look at representing integers as sums of two squares. So the first investigation is, if we start with a prime, when can a prime be represented as a sum of two squares? And we'll look at the theorem that says this is true if and only if p is congruent to 1 mod 4. Then we'll show that any such prime in fact has a unique representation as a sum of two squares. And then finally we want to characterize all integers that can be expressed as a sum of two squares. And this is kind of a fun project. You can play with examples and just test. 2 is a sum of two squares. 3 is not. 4 you can write as 2 squared plus 0 squared, and so that's a legitimate representation. 5 is 1 squared plus 2 squared, and so on. 6 fails. 7, 2 squared plus 3 fails. 8, 2 squared plus 2 squared. 9 is 3 squared plus 0 squared. 10 is 3 squared plus 1 squared, and so on. And it's a good project just to try to discover on your own when such a representation is possible. So, as an example, you may have seen a problem like this on a math competition. Can the number 1,000,003 be expressed as a sum of two squares of positive integers? Now that looks like it could be a very difficult question if you're just going to try to find two numbers that would add up to this. But with experience, we know to think about these questions mod and appropriate modulus. So in this case, let's think about it mod 4. Suppose that we had a squared plus b squared congruent to 10 to the 6th plus 3 mod 4. So in order for this to be a sum of two squares, then it would also be congruent to a sum of two squares mod 4. Well, what do we get on the right-hand side? 10 to the 6th power is 0 mod 4, so that would give us that a squared plus b squared is congruent to 3 mod 4. Is that possible? Well, if you square any number mod 4, a squared is either 0 squared, 1 squared, 2 squared is 0, 3 squared is 1, and that's it. And b squared also is either 0 or 1 mod 4. And so if you're taking an a squared plus b squared, the only possible outcomes are 0 plus 0, 0 plus 1, or 1 plus 1. You can never end up with 3 mod 4. Thus, this congruence right here has no solution, and therefore the equation has no solution. There's no solution. And this one example is pointing out a fact that if an integer is a sum of two squares, then it must be congruent to 0, 1, or 2 mod 4. So this is a necessary condition. Let n be a positive integer such that n is a squared plus b squared for some integers a and b, then n is congruent to 0, 1, or 2 mod 4. In particular, if n is an odd number, then it must be congruent to 1 mod 4. Now, unfortunately, this is not a sufficient condition. So let's consider a couple examples. The value 6 is 2 mod 4. But can we express 6 as a sum of two squares? And it's very easy to say no. 6 does not equal a squared plus b squared. 21 is congruent to 1 mod 4. But can you get 21 as a sum of two squares? So you've got 16 plus 5, 9 plus 9, and you quickly dispense with all possible things, and it's not a sum of two squares. Okay, so we don't have an if and only if statement of this type. Now, what is wrong with the numbers 6 and 21 is that when you factor them, they both have the factor 3. So 3 divides 6, 3 divides 21, and 3 itself is a prime that cannot be represented as a sum of two squares. So that's where the problem lies. So here's the theorem. If we restrict our attention to primes, then we do get an if and only if type statement. So let P be an odd prime, then P is a sum of two squares if and only if P is congruent to 1 mod 4. And moreover, this representation is unique up to order and plus or minus signs. So again, that would mean 5 you could write as 1 squared plus 2 squared, or 2 squared plus 1 squared, or you could put in negative signs if you like, something like this. Okay, proof. We already saw the necessity that in order to be a sum of two squares, the integer has to be congruent to 1 mod 4. So the real interesting part is the converse statement here. So let's start with a prime that's congruent to 1 mod 4. Now, what is special about being congruent to 1 mod 4 that we saw in the previous section? So we saw that for P congruent to 1 mod 4, -1 is a quadratic residue. Okay, so that's what P being congruent to 1 mod 4 does for us. So what does this mean? That means -1 is a perfect square. Thus, there is some integer x with x squared congruent to -1 mod P. So x squared would be -1 plus pk for some integer k. And let me rewrite this by saying that p times k equals x squared plus 1. Okay, now here's the key idea. I'm going to jump into the Gaussian integers. In the Gaussian integers, I can factor x squared plus 1 as x plus I times x minus I. And so I've got that P is a divisor of x plus I times x minus I. Now if P is an irreducible in the Gaussian integers, this would imply that P divides x plus I, or P divides x minus I, if P is irreducible in Zi. So let's consider that possibility. Can we have P dividing x plus I? Well, what does that mean? This would mean that P times some Gaussian integer, and I haven't used an A and a B yet, so let's go ahead and do that. P times A plus BI equals x plus I for some Gaussian integer A plus BI. But that means equating the real and imaginary parts. So the real part on the left is P times A, and the real part on the right is x. And then equating the imaginary parts, we'd have P times B. What's the imaginary part on the right? It's 1. And that is a contradiction. You can't have p times a number equaling 1, p times a whole number equaling 1. So we can't have p dividing x plus I. And similarly, you can't have p dividing x minus I for the same reason. Well, doesn't this contradict the Euclid type lemma we said? Well, no, it would only contradict it if p was an irreducible element. So therefore, p is reducible in the Gaussian integers. Now what does that mean? Say p equals u times v for some non-units. U and v. So remember, the Gaussian integers we showed was a unique factorization domain. So we can do all of this type of factoring for some non-units u and v in zi. Now, let's take the delta function of both sides. So u, let's write as, say, a plus bi, and v is c plus di. So delta of p is then delta of uv, and that's a multiplicative mapping. Recall the delta mapping is just the absolute value squared of a complex number. On the left-hand side you have p squared. On the right-hand side, delta of u is a squared plus b squared. And delta of v is c squared plus d squared. And u and v are not units. So this number here does not equal 1. This number here does not equal 1. So how can we have a product of two whole numbers equaling p squared? The only way that can happen, if these numbers are bigger than 1, is if a squared plus b squared is p, and c squared plus d squared is p. Therefore, p is a sum of two squares. QED. Next, let's turn to the uniqueness of representation. So suppose I have a prime congruent to 1 and that it has a representation p equals a squared plus b squared. I want to show that the values a and b are unique in some sense, up to order or plus or minus signs. So what's going on here? Well, let's again return to the Gaussian integers. This means that p is a plus bi times a minus bi. And what I claim is this is, in fact, the prime factorization of p in the Gaussian integers. Now, this was a homework problem that many of you may have already done. So what is the idea? So the claim is that these two elements are irreducible. In zi. And that follows, again, using the delta function. So you take delta of both sides. Well, claim these are irreducible. What do you do? You say, suppose that a plus bi was some u times v. Then you take the delta function. And you say, well, that's delta of u times delta of v. Delta of a plus bi is a squared plus b squared, which is p. And on the right-hand side, you have a product of two whole numbers equaling a prime. Therefore, one of these two delta values must equal plus 1. And when the delta value equals plus 1, that means u or v is a unit. Okay, so the only way to factor a plus bi is to have one of these two terms to be a unit. So since these are irreducibles, this is the factorization of p in the Gaussian integers. And zi is a UFD. So since z bracket I is a unique factorization domain, P has a unique factorization into a product of primes. And therefore, these two factors are unique. Thus, the factors a plus bi, a minus bi are unique up to the order. You can switch the order, and you can multiply by units up to, just put in unit multiples. And multiplying them by units is just changing the order of the a and b, or changing the plus or minus signs. So the uniqueness of representation is just following from the fact that p has a unique factorization in the Gaussian integers. Now let's turn to representing a general integer. So recall that if you have any positive integer, you can uniquely express it as a square free number times a perfect square. I think this was on the second homework. So how did we do that? So let's just do an example. 3 to the 7th, 5 cubed, and 7 to the 8th. Whenever you have an odd exponent, you pull off one of those factors, and that would leave you with a bunch of even exponents like this. And then for the even exponents, you can represent them as a perfect square, like that. Okay, so that's a very simple idea. Theorem. Let n be a positive integer having the factorization n1 times n2 square, where n1 is square free. Then n is a sum of two squares if and only if n1, the square free part, has no prime divisor congruent to 3 mod 4. So throughout here, let's think of these type of primes as being bad primes. Those are the primes that can't be represented as sums of two squares. So note, an equivalent way of saying this is that the multiplicity of any prime divisor of n that's congruent to 3 mod 4 must be even. So it's okay if those primes are sitting in the n2 part, but you don't want any of those primes sitting in the square free part. Okay, let's do some examples. So 45, let's factor it into its prime factorization, so that's 9 times 5. That's 3 squared times 5. Now 3 is a bad prime, but it occurs to an even multiplicity. So this is good. And what is the expression? We can do this as 36 plus 9. So 6 squared plus 3 squared. Now take 60. 6 times 10, 2 times 3, 2 times 5, so 2 squared, 3 times 5. 3 is the bad prime, and it occurs to an odd multiplicity. So that's a bad. 60 is not an a squared plus b squared. And you can convince yourself of that but with a little trial and error. 250, 25 times 10, so 5 cubed times 2. Both of these are good primes, so I don't even need to worry about the multiplicity. And 250 I can identify as 225 plus 25. So 15 squared plus 5 squared. Now for composite numbers, you won't have a unique representation, as we'll see. Okay, let's turn to the proof of the theorem. It's an if and only if statement, so let's start with necessity. Let P be a prime divisor of n congruent to 3 mod 4. We're going to prove by induction on E that if P to the 2e plus 1 divides n exactly, then n is not a sum of two squares. So if the multiplicity of P dividing n is an odd number, then n is not a sum of two squares. So we have a base case by induction on E. So let's let E to be 0 as the base case. So let's suppose P exactly divides n. And I want to show n is not a sum of two squares. Well, if n is a squared plus b squared, then P is a divisor of a squared plus b squared. So that P divides a squared plus b squared, which would mean that a squared plus b squared is congruent to 0 mod P, and that would mean that a squared is congruent to minus b squared. So if P is not a divisor of B, then B would have a multiplicative inverse, and I can bring it over to the left-hand side, and I would get A times B inverse squared is congruent to -1 mod P, which would say -1 is a quadratic residue. Aha! That's a contradiction since P is congruent to 3 mod 4. Contradicting P congruent to 3 mod 4. Therefore what? Well, therefore we must have P dividing B. Thus P divides B, and so returning to star, we must also have P dividing A. So P divides both A and B, but that would say that P squared divides A squared plus B squared. Which means that P squared divides n, contradicting the fact that the multiplicity of P dividing n is 1, a contradiction. Therefore, n is not a sum of two squares. Okay, now we do the inductive step. So suppose the statement is true for a given E, and consider the next value. Well, let's suppose it's true for E minus 1. So let's say P to the 2e plus 1 exactly divides n, and that n is a sum of two squares. So suppose n is a squared plus b squared for some integers a and b. And I just repeat the same argument. So this implies that a squared plus b squared is 0 mod p, which will imply that p divides a and p divides b, as in the base case, because -1 is not a quadratic residue mod p. Well, now that p divides a and p divides b, I come back to this representation of n, then n, and I just divide both sides by p squared, and that would be a over p squared plus b over p squared. And everything in sight here is an integer. P is a divisor of a, p is a divisor of b, p squared is a divisor of n. And so that says that the number on the left is a sum of two squares. But what is the multiplicity of p dividing the number on the left? Well, we started off with n being divisible by 2 to the e plus 1. I've factored out a 2, and so I can say that p to the 2e minus 1 exactly divides n over p squared. And so by the induction assumption, this number is not a sum of two squares. Contradicting this equation right here. QED. Okay, so we've shown that if a number is a sum of two squares, it can't have a bad prime occurring to an odd multiplicity. Now for the sufficiency. Sufficiency, we want to show that if the hypotheses are satisfied, then n is in fact a sum of two squares. And the key lemma here is the following. Suppose that I give you two numbers that are each sums of two squares. Then I claim so is the product of those two numbers. So to be explicit, if n is a squared plus b squared and m is c squared plus d squared, then the product is just this sum of two squares. And, well, you can just multiply this out and show it by brute force, but there's a natural way to think about this. So note that n is the absolute value of a plus bi squared, and m is the absolute value of c plus di squared. Thus the product is the absolute value of a plus bi squared times c plus di squared, and that's the same as the absolute value of the product by the multiplicative property of absolute values squared. And when you carry out that product, you get AC minus BD plus BC plus AD I. And that absolute value is exactly the formula we've seen. So that's the way to think about where this formula comes from. Just this multiplicative property of the absolute value symbol. Then by induction, you go one step further that say if you have k numbers, each of which are sums of two squares, then so is the product of those k numbers. So you can go on producing sums of squares by just multiplying numbers that already are sums of two squares. So to prove the theorem then, we want to show that if we start with a number n of the form n1 times n2 squared, where n1 has no prime divisor congruent to 3 mod 4, then n is a sum of 2 squares. So we want to show that n is a sum of 2 squares. And this follows immediately from the lemma we just did. So n1 and n2, so n1 is going to be of this form, p1 times p2 times pk for some distinct primes. Remember, n1 is the square free part. And none of those primes are bad. For some distinct primes pi congruent to 1 mod 4, or possibly one of them could be 2. So you've got a collection of distinct primes. Well, each of the primes that is congruent to 1 mod 4 is a sum of 2 squares, and 2 itself is a sum of 2 squares. Thus, each of these primes is a sum of 2 squares. So by the lemma we just proved, so is the product, n1. So let's say n1 is a1 squared plus a b1 squared. And now I want to represent n itself as a sum of 2 squares. Well, n is just n1 times n2 squared. So that's a1 squared plus b1 squared times n2 squared, and everything inside is going to be a perfect square. So you'll get a1 times n2 squared, a whole number squared, plus b1 times n2 squared. QED. N is a sum of 2 squares.